Okay, thank you so much for the invitation. I feel really privileged to stand here and talk about some of my recent work. Um, uh, I was a PhD student studying integer programming, but then half of my PhD thesis was about something called clutters, which can be found at the end of the title. Um, I guess it sits at the core of combinatorial optimization and integer programming. I always loved it when I was a student. But since I moved to the IE department in South Korea, I never got the chance to talk about this result, even at my department. Thanks. But yeah, and recently we got a somehow I guess I'll stick to my keyboard. Okay. We got a recently we got a nice result about this area, so I thought it's a perfect place to present this result. At the same time, it can be quite intimidating in the morning time of some day, but I'll try to, I guess, not lose you. It's okay to get lost in the middle, but just focus on the very first few slides, and I'll remind that this is the time when you need to wake up. Okay, so that's so okay. I was trying to make things as easy as possible, but I kind of figured that it's hard to avoid some technical parts when even describing these problems. So in the end, I decided to kind of give you an overview of many different topics in combinatorial optimization. So the first three parts, the first one is about perfect graphs. So there's a long history of works tackling something called the strong perfect graph theorem. That's a big area, but I will just briefly explain what it is. Okay. And the second topic is an attempt to generalize or extend this nice perfect graph theorem to the set covering problem. That's another big area, but the question is open there. So I'll briefly mention, but I'll try to give good, nice overview, easy overview in terms of integer programming perspectives. Okay. And the third one is related to the first two, and the max flow min cut property. So I guess like many of you already know the max flow min cut theorem for this kind of min cut ST pass problems, and the max flow min cut property is nothing but total dual integrality in the context of set covering problem. So I briefly mention what it is, and the last part is our is about our contributions. Okay. So let me start by explaining the goal. So if you understand this slide, it's okay to get lost in the middle. Okay. So I guess let me try to get a little bit not rigorous here, but I'll get to explain what these concepts throughout the talk. So ideal clutters is about primal integrality. Okay? But we do care about min-max theorem here. So we do care about the dual problem. So packing property. So packing property implies idealness, and it's defined as the 0, 1 plus infinity dual integrality. So the weight vectors can choose 0, 1 or plus infinity. And the MFMC property is the total dual integrality. Okay, and so there's this hierarchy of things. But the conjecture, which is called the replication conjecture, states that in fact the packing property and the MFMC property, they collapse. They are equal. Okay, so that is a conjecture that is open until now. And there's another important conjecture, which is called the tau equals 2 conjecture. I'll get to get to cover in a minute. But that implies the replication conjecture. Okay? So if you prove this tau equals 2 conjecture, you prove that these two classes of packing property and the MFMC property coincide. Okay? And our contribution is to design a class of plotters, which are called multi-partite plotters. And the goal is to find or design some classes of candidates that can serve as a, possibly serve as a counter example. Okay. So the answer, so do we have a counter example? Or I guess we have a conclusion that we cannot find a counter example from this class? Well, that is the answer of the answer that will be provided at the end of the talk. Okay. Yeah, somebody already missed this direction, but already I'm a bit worried about losing you. But okay, so this is the goal. Okay. All right. So let's go through these 4 topics one by one. So what is a perfect graph? Okay. So I'm given a graph, and I say that this graph is perfect if it satisfies the following property. So I'm taking every induced subgraph. So what is an induced subgraph? You take a subset of vertices, and you're just adding edges that are fully contained in this subset. And if the clique number equals the chromatic number for every induced subgraph, then you say that the graph is perfect. And what is a clique number? It's a maximum size of a clique, and a clique is a complete graph. So you have an edge between every pair of two vertices. And what is a chromatic number? It's a minimum number of colors so that any two adjacent vertices get different colors. Okay. And the chromatic number can be stated as the minimum number of stable sets to cover vertices. Okay. If you look at this kind of blue colored vertices, they form a stable set. Okay. Great. And the nice theorem due to Lovász in the 70s is saying the following. So if a graph is perfect, if and only if its complement is also perfect. Okay. So what is a graph complement? You're basically, if you have an edge in the graph, you just remove it. If you don't have an edge, you just add it back to the graph. That's the graph complement. Okay. And the key component of the proof is through the replication lemma. Okay. I guess I heard that Fulkerson was trying to prove this theorem, but then they couldn't find this lemma. But Lovász was the one who basically figured out this key component in the proof. And then what is the replication? So you have a graph and a vertex. So here I have V4, which is the green vertex. So what is the operation of replicating this vertex V4? So you're adding a copy of it, V4 prime. And then you are adding an edge between this copy and all the neighbors of the original vertex. You're basically making a copy of the vertex you want to replicate. And also you add an edge between the original one and the copied one. Okay. So Lovász proved this following theorem. So they have a graph, a perfect graph, and a vertex. Then, replicating this vertex preserves perfection in your graph. And you can apply this procedure of replicating vertices many times. That corresponds to taking some non-negative integer weights. So if you have a 0 weight, you delete the vertex. And then if you have a positive weight, you basically copy, WB copies of your vertices by applying this replication procedure. Okay. So as a result, you get this nice theorem. So if your graph is perfect, then for any non-negative integer weight, this graph G subscript W obtained by this procedure of applying replication multiple times is also perfect. Yeah, so you have like, if you look at this procedure, this V4 and V4 prime, yeah, that's right. Any other question? Feel free to ask any questions. I guess, but Yeah. Okay. So, anyways, using this replication lemma, Lovász was able to prove this theorem. But there's some still non-trivial component going on, but let me not talk about that here. But what I want to emphasize today is the following. So I have a graph and its complement. We have this following relationship. So the click number in the complement is equal to something called the independence number. That is the maximum size of an independent set or a stable set. A stable set and independent set, they have the same terminologies. Okay? That is because if you have a click in the complement, it's equivalent to stable set in the original graph. And you also have the following relationship. So chromatic number in the complement is equal to the click cover number. That is because chromatic number again is equivalent to the minimum number of stable sets to cover the vertices. And we know that stable set in the complement is equal to the click in the original graph. So perfection can be redefined as follows. So for any induced subgraph, you have independence number equals the click cover number. Okay. So we'll stick to this definition throughout the lecture, throughout the talk. So now let me state this definition in terms of integer programming formulations. Okay. So let me take any 0, 1 vector, and you can see that any 0, 1 vector represents an induced subgraph. So it basically takes gives some characteristic vector for a subset of vertices. Okay. And then independence number can be defined as this packing problem. So you are taking the maximum number of maximizing this linear function W transpose X, and you have this constraint Mx at most 1. And this is called the packing constraint, and X is constrained to be 0, 1. And also the click cover number can be found by solving this integer program. You can see that this the maximization program, the minimization program are kind of in the dual relationship. Okay, so we say that a graph is perfect if for any 0, 1 weight, this max problem, which is the packing problem, is equal to the mean value. Okay. That is, so this is the integer programming definition for perfect graphs. Okay. Great. So let me kind of repeat what I just said. So suppose that for every 0, 1 vector W, we have this like max mean relationship. Okay. Again, the independent set number and the chromatic cover, the click cover number. And it means that the graph is perfect, right? Then now, because the graph is perfect, we can apply the replication lemma. Okay. Now what we do is we take any arbitrary non-negative integer vector, and then we apply the replication accordingly. Then because this graph after replication is perfect, we still have this equality. The independence number equals the click cover number. And it's not hard to see the following. So for any non-negative integer weight, this graph's independence number and click cover number can be found by this integer programs. But right now I have like non-negative integer constraint for y, because the W here can be arbitrary non-negative integers. Okay. And because these two numbers coincide, we have this relationship. Okay, so we have this max-min relationship for any non-negative integer weight. Okay, again the connection. So if you go from the assumption, so we looked at the 0, 1 weights, and we applied replication lemma, and we somehow the same relationship for non-negative integer weight. Okay. So that's the corollary. So let's say this max-min relationship holds for any 0, 1 weight, then It holds for any non-negative integer weight. Okay, so this implies that 0, 1 dual integrality implies total dual integrality. This is not always the case, but for this class of problem, this is true. And in fact, this is not just for graphs. You can take any 0, 1 matrix M, and this statement is full. It's true. Okay. And for any arbitrary 0 matrix M, you can generalize the concepts to like columns and subset of columns and so forth. All right. Then now we are ready to, okay, and this is for set packing problems again. So you have this mx at most 1. So you're allowed to pick a certain number of vertices to satisfy this at most 1 constraint. Now we are ready to state this replication conjecture. Okay? So let's take an arbitrary 0 matrix M. Now I'm using this notation E to say like to refer to columns, and I'm taking some subsets of columns. So rows correspond to this family C. Then suppose that now we have min-max relationship for any 0, 1 plus infinity weights. Okay, so if you look at this left-hand side, I had max problem before, but I have mean here. And I had mx at most 1 before, but I have mx at least 1. Okay, and if you look at the right-hand side, it's the dual of this left-hand side problem. Okay, now let's suppose that this min-max relationship holds for 0, 1 plus infinity. Then the conjecture states that this is true for any non-negative integer weights. Okay. Again, for this problem, the conjecture is that 0, 1 plus infinity dual integrality implies total dual integrality. Okay. And this is called the replication conjecture because it's a set covering analog of the replication lemma. And mx at least 1 requires a cover, and in computer science, people refer to it as a heating set. Okay, you are basically taking a subset of elements that intersect every members in the family C. Any question? Okay. So if not, so for the second part, I'll be focusing on this set covering problem. So right now we stated the conjecture in terms of integer programming, but let me give you a little bit of its combinatorial interpretation. So let's say I have a finite set of elements, okay, and I take some subsets of these elements, and I say, and each subset is called member. Okay. I'll use these terminologies. And there's this notion of clutter. I always feel this definition a bit kind of arbitrary, but let me explain like why they use this notion. So we say that this family is a clutter if no member contains another one. So if you look at so if you take some family of subsets of E, now you take the inclusion-wise minimal ones, then you are getting this clutter. If you take because everything is minimal, no set contains another one. It makes sense for set covering problem using this. If you look at this example, so I have 6 elements set E, and I'm taking 3 subsets. Okay, and then if you pick these 2 middle black vertices, they will intersect all this purple, green, and red one. Okay, so if you this 2 thing becomes a cover or a heating set. Okay, now let's say I take a subset of the bottom 3 vertices, which contains this red one, right? But if you intersect this red one, then it will automatically intersect this superset. So it doesn't make sense to contain something containing another subset. So it makes sense to include only inclusion-wise minimal ones. That's why we are just taking this clutter definition. Okay. There are many nice examples in graph theory. So you take 2 vertices S and T, and look at ST paths, they're also inclusion-wise minimal. Okay, and also if you collect all spanning trees in a graph, it also forms a clutter. Okay. Great. So now I need to define another arbitrary notion. So I have a clutter, and let's say I have a subset B that intersects every member in my family. Then it's called a cover, or in computer science, it's called a heating set or a transversal. Okay. Now let me take all inclusion-wise minimal covers. Then that's called the blocker of this clutter C. Okay. If you see this example, the definition may look clear. So if you take the blocker of ST path, it becomes minimal ST cuts. Okay. Now we need to take minimal ST cut to form a blocker. Okay. And also if you take spanning trees, its blocker is a set of minimal cuts. Okay. If you destroy all spanning trees, then the graph becomes disconnected. Okay. And this nice theorem is saying that if you take the blocker of the blocker, then you get back to the original one. Okay. Right. So there are some motivations, like there are kind of two-player games. So one player kind of presents some set of winning coalition, and the other player tries to destroy it. Also, network interdiction. So there are one player tries to connect two distinct nodes in your network, and the other player tries to destroy this connection. Okay, so the second player will win if it kind of completely destroys the connection in your network. So the question is, what is the minimum size of a cover? Okay, so for the second player, it needs to find the minimum number of edges, arcs, to destroy the graph connection, or network connection. Okay. Great. So we do care about this, minimum size of a cover throughout this talk. So, okay, just to look at general clutters, we have a clutter C. And the minimum size of a cover is denoted as this tau of C, which is called a covering number. Okay. The related notion is the packing number, which is the maximum number of disjoint members. Okay. Now there's a nice relationship. So the covering number is always lower bounded by the packing number. That's because if you have like disjoint members, to intersect every single one of these disjoint ones, you need at least one element from each of these sets. That's why we have this inequality. But in general, the inequality is strict. Okay, so if you look at this example, I have edges of K4, which is a complete graph on 4 vertices, and I take triangles. So I have 4 triangles in K4, but to intersect all these 4 triangles, I need at least 2 edges. That's why the covering number is 2. But there's no 2 disjoint triangles in the graph. That's why the packing number is 1. So the inequality is strict in this example. Okay. And this is called Q6, and this example will appear in many of our theorems later. Right. Okay, so one question in theoretical computer science is the following. So when is it that the covering number is upper bounded by some constant multiple of the packing number? So when we have these inequalities. But our question for combinatorial optimization is that when is it that these two numbers are equal? I want the exact statement, not the approximated statement. Right? So we say that the clutter packs if the equality actually holds. And, for the clutter of an ST path, we have this following statement. So the minimum size of an ST cut is equal to the maximum number of disjoint ST paths. Okay? We all know this kind of nice theorem from network flows and graph theory and discrete math, and this is due to Menger. So this theorem is called Menger's theorem. And also, Lucchese and Younger proved the following. So the minimum size of a dijoin. So dijoin is, you have a directed graph, and if you contract all arcs in the dijoin, then the graph becomes strongly connected. Okay, and that's equal to the maximum number of disjoint die cuts. Okay. Okay. But let me tell you the following. So this question of when does this clutter pack may not be well defined. Okay? Let me give you some example. So I have some two arbitrary clutters C1 and C2, and I can embed these two kind of arbitrary clutters in a way that the resulting clutter packs. Okay? So if you look at this example, I have the one clutter on the left, top left corner, and I'm adding one column which has all ones for the first set of rows, and I have the second clutter, and then another column of all ones for the second part. Okay, the covering number is 2 because I can take these two columns and they will intersect all these members. But the packing number is also 2. I can take any arbitrary row from the first part and any row from the second part. Okay, so the covering number, then those two rows will be destroyed. Okay, so this is some kind of a stupid example to make your clutter pack. But then we want to avoid this construction because there are something kind of arbitrary going on inside this construction. So I want to avoid this construction. So to look at this thing, I need to define some minor operations. So I want to discover this kind of arbitrary structure inside, and I want to avoid this thing. Okay. But how do I get to these two arbitrary clutters? Well, so contraction is, so you remove this column, okay, and then you take the include-wise minimum ones. And deletion, let's say you delete this thing, okay, then you remove these columns, and you also delete rows containing these ones. Okay, so if you contract this thing, and then if you delete this thing, then you remove this second part, and you keep the first clutter. And at the same time, if you contract this thing, and then delete the first one, then you keep the second part. Okay, so these minor operations will get you to this kind of arbitrary clutters which are hidden in this big clutter. Okay. And a minor of this thing, it can be something called, is anything that can be obtained by applying these contractions and deletion operations. So again, this example has a minor as the C1 and C2 as a minor. Okay. So maybe like maybe more meaningful definition is the following. So the clutter has the packing property if every minor of it packs. Okay. This is how you avoid this construction if this C1 and C2 do not pack. Okay. And it's a closed minor closed property. So and you can take minor and minor operations. It's called minimally non-packing. If it doesn't pack, but every proper minor of it packs. Okay? It means that if your clutter doesn't pack, then you have to have some minimally non-packing minor. At some point, the clutter will be trivial and it will pack. Okay. So what kind of properties do we have? Gerard and Bertrand and Francois, like 25 years ago, proved the following. If you have a clutter that has the packing property, then it is ideal. And I didn't define what it means to be ideal, but it means primary integrality. I'll get to the precise definition later. And also idealness is also a minor closed property, meaning that, if you have an ideal clutter, every proper minor of it is also ideal. And you say that a clutter is minimally non-ideal if it is non-ideal, but every proper minor of it is ideal. And you can prove that every minimally non-packing clutter is either ideal or minimally non-ideal. So if you take if you take a clutter that is almost having the packing property, then it is almost having the idealness property. That's what it means. But we have a nice characterization of minimally non-ideal clutters. So we understand the second class fairly well. So what about understanding the first class? So minimally non-packing and the outcome is ideal. That is the question. So let's consider that clutter that is ideal, which was the first outcome of minimally non-packingness. Then this conjecture, which is called the tau equals 2 conjecture, says that the covering number has to be 2. That is the conjecture. Okay. This looks quite simple and quite arbitrary, and there's no clue why this is true. So I guess the aim of this talk is to provide a counterexample to this conjecture. Okay. I'll get to that later. But we have this replication conjecture before, but in fact, it's known that this conjecture, if it's true, it will prove that this replication conjecture is true. Okay. Somehow, like these two are kind of disconnected, but somehow like there's a nice relationship behind it. Okay. So I'll briefly talk about the max flow Mincup property. Okay, just to motivate, just to kind of give you more intuition why. So Seymour defined this notion of max flow Mincup property, which is nothing but the total dual integrality. Okay. So, and if you take the clutter of ST-paths and the clutter of dijoins, they have the packing property. They have the total dual integrality for our set covering problem. Okay, and the packing property can be written as a subclass of the MFMC, the generalization of the packing property, MFMC property. So we say that the clutter has the packing property if this min-max relationship holds for 0, 1 plus infinity weight. Okay. So which means that the MFMC property implies the packing property. And, now let's define the idealness. I said that it's equivalent to primary integrality. So we say that a clutter is ideal if this thing is whole, okay, for any non-negative integer weight. So I have this dual linear program. The primal linear program has an optimal solution that is integral. Okay. This is why idealness is primary integrality. Equivalently, a clutter is ideal, and if you take the non-negativity constraints and this covering constraints, then this thing defines an integral polyhedron. So let me recap. So we have this hierarchy of properties. So idealness, primary integrality, packing property is 0, 1 plus infinity dual integrality. And the MFMC property is a total dual integrality. And we have explained the replication conjecture. Okay. So the conjecture means that these two classes coincide. And the tau equals 2 conjecture has this thing. Again, the clutter is ideal and minimally non-packing. Then the covering number is 2. And then this thing implies the replication conjecture, which is due to Gerard, Bertrand, and Francois. Okay, so now it's time to wake up. Okay, I have 10 more minutes. So I guess the last part is about how to tackle the tau equals 2 conjecture. So we studied I had on kind of intuition that, this is kind of too arbitrary and the tau number is too small. Maybe you can find a counterexample. So that's our initial motivation. So we were trying to look at this tau equals 2 conjecture. So the question, yeah. Sure.
So disproving this conjecture doesn't imply disproving the other conjecture.
You're right. Yeah. But I guess like Ahmad had a different interpretation. Maybe he was trying to find counterexamples, and then at some point you don't, like you just kind of all possible small examples. Then there will be a kind of strong, indication that this conjecture is true and the replication conjecture is true. But I had a different intuition. Okay. So, any other question? I guess I'm right on time. Right. So again, I have this kind of properties, idealness and minimally non-packing, and would it be that the covering number is 2? Okay. So the question is, can we construct the ideal clusters? So let me forget about the property of minimally non-packing. Let's focus on the ideal part. Okay. And can we construct a cluster whose covering number is greater than 2? That's even possible. And that was our question. There's a nice class of clusters to make covering number large. Okay. Now let's look at this example. Okay. I ask you to focus on this example because this is the key part for our results. So we have this element set. So the element set E is decomposed into this n disjoint subsets, and my cluster is called multipartite if every member contains precisely one element from each of these n subsets. Okay. It's an extension of the bipartite graph. Okay. Right. So again, so every member in my family is intersecting each of these subsets. Then I call the cluster multipartite. Then then each subset gives you a nice cover. If you have kind of many elements in this set, then maybe like the cluster has a high number of covering number. There could be other covers as well, but again, at least from this point of view, the natural covers are these subsets, and they have large cardinalities. Okay, that is the thing. So then the question is, can we construct an ideal multipartite cluster? Somehow, maybe I can handle the high covering number side, and I want to make, the next question is, can we make it ideal? So that I can have the property of idealness and large covering number. The first part is the following. So we focus on the set of 0, 1 vectors for now, and we are collecting a set of solutions satisfying this equation, modulo 2. And this thing is called a binary space, a vector space in the binary fields. Okay. For example, if you have this hypercube of dimension 3, I'm taking, let's say, these 4 vectors, 4 points in this kind of 0, 1 hypercube of dimension 3. What I do is the following. So for each coordinate, I have n coordinates if you have dimension n. For each coordinate, I have 2 possibilities, 0 and 1. So to encode the information, I introduce 2 elements for my cluster. So we have n-dimensional space. We have 2 elements in cluster. Okay. So there are 2 possible values. So for one coordinate, I associate 2 elements as the following. So I have 0, 0, 0. And let's focus on this coordinate of value 0. I assign 1, 0. Okay. I have 3 dimensions. So I have 6 elements in my cluster. But 0 corresponds to 1, 0. And 1 here corresponds to 0, 1. Okay. And this generates the cluster of triangles in K4. Okay. So this construction contains many of nice examples in this set covering problem. Okay. So we proved like 5 years ago the following. So the multipartite cluster that can be generated from this hypercube or binary space is ideal if and only if it has the following list of clutters as minor. Okay? You don't have to remember the statement. It's like, there's kind of L7 is like 7-member family that correspond to the lines of this Fano plane. And this O5 is a clutter of all circuits of K5 and its blocker. Okay. We can characterize idealness of this multi-partite clutter in terms of this excluded minor statement. Okay. So, but, binary space, by definition, has covering number 2, because you can take any two columns here that will cover everything. So, but our goal was to set covering number at least 3. So to achieve this goal, we are generalizing this concept of binary space into any prime power Q. So what I want to do is we look at vector spaces in modulo Q, where Q is an arbitrary prime power. Okay, that's how we are trying to make this covering number large. Okay. So if you construct the corresponding multi-partite clutters, so okay, basically one coordinate has Q elements. Okay, so we have n dimension, so we have Qn elements in total. So an example is the following. So we have, let's say, so 3 possibilities for one coordinate, and 3 possibilities in one coordinate, and for the other coordinate we have 2 possibilities. So one example can be written as expressed as this picture. Okay. Then if you look at the clutter, we have 3 columns in one part, and 3 columns in the second part, and 2 columns in the last part. Okay. This is one example. And so we look at this class of clutters. Here's our theorem. So the previous theorems, was for the case Q equals 2. But let's look at Q is odd or Q equals 4. Okay. We proved the following. So the associated clutter is ideal if and only if it has this triangle clutter as a minor. 1, 2, 2, 3, and 3, 1. So all primes are done, and Q equals 4 is done. Remaining case is power of 2 greater than 4. It is ideal if and only if the C5-2 as a minor. This is a cycle of length 5. And even for the next Vlov-Minkoff property, we found the following theorem. This is true for any prime power, including Q equals 2. Okay. It has the MFMC property if and only if the clutter has no delta 3 and Q6 as a minor. Okay. So we have a complete understanding about this multi-partite clutter construction. But in fact, based on these characterizations, we ended up having this conclusion that the conjectures are true for this class of clutters. This can be a bad news for me because it means that we cannot find the counterexample to the conjecture. But maybe it's a good news for, I guess, Ahmad. It means that, maybe it's a strong proof, evidence that the conjecture is true. Okay, so this is it for today. And thank you so much for your listening.